All right, I want to wrap up the gravity lab that we started the other day, and in that lab there was you would have some mass like that one, and another mass like that one. And there would be some distance that we would measure between them. So we would be going from center to center, and there was some distance that separated these two masses. So this will be mass 2 over here. This will be mass 1, and I think we'll just have this be a 50 kilogram mass like you see on the other screen that's not being recorded, and this is a 200 kilogram mass, right? So distance 1, when it's 4 meters, we have force 1 on 2 and force 2 on 1 are the same magnitudes. All right? And in this case, it's we'll write these as magnitudes are equal. Let's see, 4.17 times 10 to the minus what? 368 newtons. So we have those two things, and if we were to change the distance to 2 meters, so when distance 2 is 2 meters, then the magnitude of the force ends up being 1.6889 times 10 to the minus 7. Check that. Yeah. So it went down by a factor of 10 when I cut the distance in half, which you're going from a 16 to a 4, so you are changing a power of 10, so that makes sense. So we have these measurements that we would obtain if we did a hands-on experiment, which are somewhat time-consuming and complicated to set up, right? Expensive equipment, so it's better to just trust that this is the way that it works, and it fundamentally is. And so what we have here, as discussed the other day, you have a pair of forces. You have force 1 on 2 and force 2 on 1. These are both vector quantities. You have a distance from 1 to 2 and a distance from 2 to 1, but these are also vector quantities even though their magnitudes are the same, okay, in any given situation. And then we have mass 1 and mass 2. So there are 6 quantities at play in each one of these force interactions. And as we determined yesterday, force was directly proportional to mass in this situation, and force was inversely proportional to the separation distance. Okay? Using D and R, D for distance, R for distance. Same thing. So we have these proportionalities. All right? So what do we do with that? So the way that this plays out when we have force proportional to mass and force inversely proportional to the distance. We would write a identity for the dependent variable, and then we would multiply one side of that, usually the right-hand side since we like to go left to right, by fancy forms of 1 of all of the all the variables that interact. Well, we have mass 1 and mass 2, we have distance 1 and distance 2. So mass 1, fancy form of 1, mass 2 as a fancy form of 1, distance 1 and distance 2. Still an identity, force equals force, which we've seen that several times now. Newton's third law, equal and opposite pairs. Okay, we're dealing with magnitudes right now, so we know that the magnitudes of the force have to be equal. We see that they are equal when we run the simulation. But now we need to encode for these. So this right here, the fact that force is directly proportional to mass, we see that right here. We see that force is directly proportional to mass in that one. The inversely proportional to distance, we see that here. That's what it means to connect these two equations, or to connect the proportionalities with the equation. So in the lab, I ask you to group the interaction variables, and the interaction variables are the ones that have a dependency. Those are the interaction variables. And so if we were to do that, the forces aren't going to move anywhere, but I would have, since force on the right-hand side of the equal wasn't part of the interaction variable, I'm going to move those distances and the masses into a group with the things that aren't part of the proportionalities. Okay, they're not following the proportionality template here that we got from experiment. And so mass 1, mass 2, and distance 1, distance 2 make it over there. So here we have, these are the interaction variables. Okay, that are connecting to the proportionalities. Okay, that's why we're calling those the interaction variables. And then there's the rest of this story. The other part that's left over is going to be our constant of proportionality. The last time that we did this lawmaking scheme and got a constant, it was on one of the simplest things that you could possibly use that tool with, the circumference diameter relationship of a circle, which we knew to be pi going in, but we perhaps were not as fully aware that pi is a function relating the circumference to diameter, and no matter what circumference you pick, the diameter that goes with that circumference will always be in this pi relationship. So it's the law of the circle, if you will. Pi is the law of the circle. And then now we have the ability to construct a constant, okay, that goes into this lawmaking business that we're used to. So it is the case that this constant of proportionality is Newton's gravitational constant, capital G. And one of the things that we can do, it is the case that D1, the magnitude of it, equals the magnitude of D2. So we can just define that to be D. And so we have a D times a D, so we have a D squared here. This is the classical form for Newton's law of gravity. And it relates the masses of the objects in that force interaction and the separation distance between them. It's classically understood to be an inverse square law, and the reason that it is an inverse square law isn't just because it has a d squared denominator. The reason that it's an inverse square law is because you have two distances that are in an inverse relationship with these reciprocal forces. So you get a d times d in the denominator by necessity. All right? It is the case that the best fit function is an inverse square function. However, if you, we can show this later, if you were to say, try to fit it with a cubic function, or a quartic, or a quintic, etc., you would keep getting a higher correlation, so to speak, in your graph, but what you'll start getting is wobbles in the graph that aren't physical. This is a smooth, continuous inverse square function. And whereas a cubic would give you some bumps, but we don't notice those bumps in reality. So we'd be getting a better fit by the numbers of a trend line in Excel or whatever we chose, but it wouldn't be physical. It would violate what we observe, whereas the inverse square doesn't violate it, the empirical data, and it also fits the way that this interaction is constructed. All right? So it's an inverse square law because of what I just showed. All right? There are more complicated ways to talk about the structure of a law like this. This is the least complicated way. All right? And so if we were to plug and chug the values that we had from the other screen. All right, here we go. So force D1, D2, M1, M2. And so for one of our options, we had 4.1712 times 10 to the minus 8 times a 4 meter, and a 50, and a 200. So let's pause and give, what is that going to equal as a number? So if you crunch this correctly, you will get 6.67 times 10 to the minus 11. Now the units are going to be Newton meter squared because you have a force and two distances per kilogram squared. That'll be the units of this thing. Now if I take the other force, distance, mass pairs, then I get the same number, well, some of the same numbers. Still have the 50 and the 200 mass because we didn't change that, but the distance has changed and the force has changed to 1.68189 times 10 to the minus 7. Got a little bit different answer on this one, 6.72 times 10 to the minus 11. It would have been exactly the same. I probably wrote down the force number wrong, got a decimal place out, but it was too far out in it to make a difference. So basically, if we were to go look up the value, we would get 6.67 times 10 to the minus 11. A lot of people just write 6.7 times 10 to the minus 11. That is the numeric value of Newton's big G gravitational constant. All right, so we would get it from experiment. Now we had a simulation that makes it easy to get the numbers, but this basically does the same thing in a much shorter and easier time frame. So it is the case that Newton's gravitational constant, the one that shows up in the F is g mass 1 mass 2 over distance squared, that is Newton's law of gravity, and big G is that constant that essentially preserves the identity. Because remember, this F d squared per m squared thing, that is big G, was just a rearrangement of all the fancy forms of 1 for the things that were interacting. We separated out the stuff that was directly and inversely proportional. The rest of the stuff was the conversion factor. So we still get force equals force. So if we're going to solve for a force, it has to be a force, and all of those mass-distance ratios basically just keep that identity going so that I actually have a force, but I understand the components or the elements, so to speak, of that force.